Well, hi, good morning. Thank you so much for coming and keeping me company in my shop here while I take a look at this box radio. So I took a peek at this on the end of the last video and was surprised to find out this thing is full of tubes. Here it is. Oh, not so much to look at, but very silvery RCA Victor AM radio. Tuning, volume, speaker, a couple of copper bands here heading up into this area. This is where the antenna is going to be. All metal can, but this is a plastic top. When you pop it open, the antenna is sitting out here away from the metal can. So I've already popped the bottom off of this. So we'll just pop it off again. So you need to pop the bottom off to put batteries into it. It's come with this information. It shows what tubes are involved. These are 1-volt tubes. A little bit precarious, I would put it that way. A little mistake, you can burn these tubes out, and I'm saying that from experience. Unfortunately, the top of the paper has been eaten away by chemicals that have leaked out of batteries previously. So we can't see from here what the model number is, but I did find it. I searched for this by looking at photographs on Radio Museum and found it. Okay, this is pretty old, because down here is the requirement in Canada at that time to have a license to operate this radio. So we know it's during the war times, or maybe shortly thereafter. Okay, so we look inside. Oh my gosh, they've installed everything upside down. Well, maybe it'll look better this way. So there's quite a lineup of tubes in here. 1, 2, 3, 4, 5, 6 tubes. And you're going to power 6 tubes from batteries. This can't be plugged in the wall. There's no cord, there's no power supply like that. One of the batteries sits here. This would be a single cell. This would be like an ordinary 1.5 volt batteries. Actually, they're 1.6, I believe is the truth. Be sitting here. And this would power all the heaters in these tubes in parallel. And holy smokes, you can actually heat up all these tubes with a single battery and get some life out of it? Yes, you can. These tubes are designed to be battery operated, and they're designed to draw very little current. The heaters use very, very little power. So even though there's a lot of tubes in here, 6 tubes, this one battery would probably keep them going. Well, obviously it would keep them going long enough to make it worthwhile. You know, by the time you get to the beach, the radio doesn't work anymore. I don't think that's the case. It has these two special looking clips. These will go onto a battery case or a special battery. A special battery would be sitting right in here, and this battery would be putting out a high voltage, 45, 67, or sometimes 245s for 90. This radio is built for 67 volts, so there'd be a battery in here for 67 volts. Now, not much current is drawn from the high voltage battery. This one is the one that's going to wear out. So you might have to replace this a number of times before replacing the high voltage battery. When, of course, the high voltage battery is long gone. And where are you going to get a 67 volt battery today? Well, I don't know. Maybe there's somebody kind of remanufacturing them in a way, somewhere out there. But for me, I'll just power this with shop power supplies. But I won't do that here. I won't put a power supply on here. I put a battery in here, or hook up a battery somehow. Just a regular D cell. And the reason for that is, it's an absolute guarantee you're not going to drive over voltage onto the heaters of these sensitive tubes. You use a power supply with a voltage control, and make a little mistake, and all those tubes are shot. And again, I'm speaking from experience. Only when I blew a whole set of tubes up, it was a big mistake I made. It wasn't a small mistake, but that's made me very gun shy of these tubes. Those two of them are in shields, the rest are not. And you gotta wonder, why so many tubes? There's no need to rectify power. It's coming from a battery. So either this is a really good AM radio, or for some reason it's got more tubes than needed in it. I don't really understand that. So we can see some of the capacitors here. They all look original. 1, 2, 3, 4, 5. I can see 6 just right in here, and they all look original. So it looks like nothing's been done to this radio. So probably what happens in the life of a radio like this, a battery operated radio like this, is the 45 volt battery wears out. You're going to buy another one of those, keep that old radio going with the tubes in it. Why not get a brand new 5 transistor Japanese radio and do away with this? Well, it's kind of cool looking, so we'll put it on the shelf. And there it's been since then till now. This radio is probably not operated, well, assuming it was made in the mid 40s. Let's take a guess. I think it's actually early 40s. Let's say mid 40s. So that'd be 40. So from the mid 40s to that would be 60. Might be maybe 60 years, something like that, since this radio's had any juice in it. I should juice it up. Is there any reason why I wouldn't power up this radio carefully and see if it works right now? Not that much. There's not much reason for that. Another way these radios die is one of the tubes quits, and that's it. And it stops working, and I don't want to buy another battery. I don't want to deal. Yeah. Give me that Japanese radio, please. This might have been made in Japan even. Where was this built? Can we find out? Is it going to tell us anywhere? Maybe here. So if you're caught using this radio without a license, you may have to forfeit the set to His Majesty. Hey, there's a His Majesty again. By order of the minister. Made in Canada by RCA Victor Company Limited and licensed. So this is built here in Canada. 1932 patents it's referring to, but I think this is from 1941 or so. Okay, power it up. Might be worth looking at the schematic for this first before we do that. Let's take a look at the schematic and just see what we can see there. Okay, here's the schematic on this page. Let's take a look at just a few notes here. Installation instructions for lid or control panel. So this surface is called the control panel, even though it has only one control on it. So just instructions on how to take this top part off. Why would you want to do that? Install a new lid or new front panel using replacement hinge pins and springs. I guess this part gets broken. It gets maybe ripped off, damaged, or something like that. It seems odd that this would be a concern. But anyway, here's the battery compartments shown here. Sure enough, 1.5 volt A. Oh, an A battery. An A battery. So these days we have D cells and C cells. No B cells floating around. No A cells. What's in it? So I don't know if this is the same as the D. And then here's the other battery. 67.5 volt B battery. Now you know where B plus comes from. The B refers to the B battery. Ever-ready cell. Okay, instructions on alignment. That's good. Okay. Now we'll take a look at the schematic itself. So these may be low voltage tubes, but they're complex inside, no doubt about it. How come there's only one? Oh, these two tubes aren't tubes. Okay, that I thought there were two shielded tubes in there, but they're not. They're the IF transformers. Okay, you probably knew that when I was pointing at it. That makes more sense now. 4 tubes. That makes much more sense. So we look at the antenna here. This is what's hidden in the lid. This looks like the antenna coil. Oh, oscillator coil. There is no antenna coil except for what's in the lid itself. That's connected to grid 3 on the converter tube. Grid 1. Interesting. Grid 1 is grounded. Okay, the grid 2 is being used to enable the oscillator to operate. Oh, you know what? This tube's upside down. Okay. Okay. I didn't notice that. Yes, they've drawn the tube upside down. Well, it's probably because, as I showed you, they installed them in the can upside down, so they've shown them upside down too. Let's start over now. This makes more sense. Grid number 1 connected to the oscillator through here. Very good. Grid number 1, 2, 3 connected to the incoming signal. That's just typical. Screen grid here and here. There's 2 screens in these tubes, and a suppressor is grounded. Okay, that all makes sense. Didn't make a lot of sense there at first. Very good. So the output from this tube goes into the IF transformer, out into the grid, IF amplifier, out into here, another transformer, and we're into the detector. The detector has only one diode. It's being used here. The DC that's going to build up in here, what do they do with it? They stick it through a resistor, through a great big resistor, and then on this side are all the grids. And look right through the loop antenna to get to the grid. So a lot of these radios do that. The AVC voltage goes right through the windings of the loop antenna to get to the grid. Very good. Okay, this will be the AVC capacitor here. And these ones are all about snuffing out the RF that's remaining after detection, or providing an RF ground at the bottom of this coil. Volume control. Again, that's the DC blocking capacitor there. So they're letting the rectified IF output DC go right across the volume control. And there's a huge resistor here, typical. And then the signal, which is now mostly or entirely audio, sent up here to an audio amplifier. The triode here, and the output comes along. This capacitor's job is to get rid of any RF that might still be there. And then we pass the signal. This is quite a small capacitor compared to this one. So this can also be preventing oscillations, high frequency oscillations and other stuff from taking place. So take everything I say with a grain of salt as I say it. In fact, you should have the salt shaker in your hand while I'm talking. And so the audio is sent to the grid at the output tube. And then from here, it comes down through the coils of the output transformer, and then off to the power supply battery. Here it is. Notice the switch S1 on lid. Oh, I see what's going on here. You open the lid and it turns on. Close the lid and it turns off. So there's the on-off switch. I kind of wondered where it was. It's arranged on the lid. Bet you this gives trouble in some of these sets. You notice there's two switches. They're applying a ground on this end of this battery and also on this end of this battery. So these two circuits are switched separately. In some of these radios, they actually leave the high voltage battery connected all the time, because all it does is run to plates in tubes and screens, and then when the tubes are off, there's no current flow. So the battery can remain, just puts a charge on these elements, but nothing happens because of it. This one has a switch. Okay, there's a great big capacitor here, which is probably to drain signals. That's a screen line here, so this is to drain the screen. Otherwise, you're connecting the screens all together in these in these different tubes, and they would start passing signals back and forth, and that would lead to a lot of weird stuff. So this is trying to hold down the de-signalize this wire, so there's no signals on it. So it's a very straightforward radio. Nothing particularly surprising about it. It's really almost a textbook radio the way it's built. Very good. Well, should we turn it on? Should we turn it on here? Output meter, test oscillator. It's just all about alignment here. And there's the actual model number, BP-10A. Battery portable, number 10, version A. There's more versions to this. Very good. Okay, fantastic. I'm gonna go drink a little coffee, and then I think we're gonna try and start this guy up. Okay, so I'm making a little battery holder, I guess. Putting some clips on a battery holder here. Trying to make this convenient. Go. Okay, not much of a contact here at the top. Definitely there. Let's check and make sure this is producing what we think it is. .6 volts. It's a brand new battery. Okay. Oh, we're going to need this meter. the next thing we're going to do is set up the 90 volts. Be 90 volts on the end of these. Not 90, Jim, 67. Actually, we'll probably do 60. I'm going to just follow the wire up to this guy here. And with the leads not connected, I have to let this warm up a little bit. So we'll set the open circuit voltage. There's hardly any current draw, I imagine. Well, I don't know. Okay, so I'm going to watch this meter. Again, it's hooked up to nothing. This is the voltage. I left this dial up. Shame on me. I turned this on with this dial up and stuck on the end of those wires almost 200 volts. Oh. Bad operator. But because I didn't have it connected to anything, good show. Now we're going to measure the actual voltage here. Because the voltmeter up there is on the instrument is really pretty rough. Minus 28. I'm gone. Look at that. Isn't that? If there's a way to make a mistake, I'll make it. That's why I'm really into double checking. So 28 on here. Volts. Oh, you know, 20, about 25 on there. Okay, let's go up to say 60 volts or so. Okay, so there's 60 volts. Why not 67? I don't know. Now we're going to cut the power off from here, and we're going to want to monitor this the whole time. So I'm going to use clip leads to go from here to here. Now, positive and negative. Well, there's a red one and a not red one. And it really has to be the case the red one is the positive. What if I get this backwards? Probably no consequence, except nothing's going to work. Now, there's no voltage here right now. All I got to do is connect this here. We're in business. Now this battery, there's a polarity issue with the with this battery too. Look in here. Probably it's rusted away. This lead is actually kind of just free here too. They can guess this is the positive because of the shape of the connector here, and this would be the negative. That's a good guess. So we're going to cut the positive on here. Now, should we measure the current coming through this battery, from this battery? We probably should. We probably should. So I need another meter for that. Look in this here. This is a clamp-on meter with a dead battery in it. Clamp-on meter, and it reads down to, well, I don't know if it can read such a small current. You know, these kind that you read through here, they're affected by the Earth's magnetic field, and very tiny currents not going to work so well. So why don't we try one? Okay, so I'm gonna stop the video while I sort this out. Okay, let's just see what we've got here. So I've got this battery ready to drive the heaters. Got one wire connected. The other wire appears open. This black wire from the battery goes through this cable over to this meter. The meter is set for current in milliamps. It's going to read it on here. This connection just needs to go on here. Let's put it on there. There should be no current flow. think I shorted it just for a moment there, and that's why you saw a flash. No current flow, if I've done this correctly. Now on the voltage side of things, I'm going to reduce it on the panel up here. So this is set to nothing. So we're going to just turn on the radio, no B+. We're going to watch and concentrate on what's happening here. So turning on the radio. Now I got to open up the lid. How far do you have to open the lid to have it come on? I think we're going to find out. Okay. There. Overload. So it's drawing more milliamps than the scale here. How can this be an overload? Can it be drawing more than a... Well, according to where the dot is, this is good for about 99 milliamps. Is there another setting here? I don't think so. It's only milliamps. Are there scales? AC? DC? Well, okay. I gotta get a different meter. This one can't do the job. Okay, let's try this meter. Now this time I've got this set for the 10 amp scale. Surely to goodness, no 10 amps is going to come out of this thing. And we'll find out this way, as soon as I remember which wire to connect. Oh, it's a matter of opening the lid at this point. Okay, here we go. 1.3 amps. You got to be kidding me. .3 amps. How long is the battery going to last like that? So with these tubes, you cannot see when they're lit. They're just, the heaters are too tiny, and it's 1.3 amps. I don't know about that. So 4 tubes in parallel. What kind of current do they draw? One is a 1T4. Now these are not in series, so they could all have different currents. 1T4. 1S2. Oh, look, they're all listed here. Refer to chart at end of section. Oh, that's great. Give me a page number. There's a chart at the end of the section. What section? This whole section here. Yeah, I'm going to flip to my other book. Because, yeah, this is where it's going to be. See, they tried to make the book more efficient. But it makes it more awkward. Like less paper, but it makes it more awkward. 1T4. Volts, 1.4 volts. And I've got 1.6 coming off that battery. Amps, 0.05. So it's 50 milliamps. Oh, here's a 1T6, 40 milliamps. A 1U4, 50 milliamps. 1U5, 50. A 1R, 50. 1S4, 100 milliamps. A 1S4. So 100 milliamps or 50 milliamps. So that should be, say, 200, 250, 300 milliamps. Somewhere in the range of 300 milliamps. What's going on here? 300 milliamps, but I'm getting 1.3 amps. So got to be a shorted tube. Shorted tube. Well, you know what that says? It says we got to test these tubes at this point. We can't go any further without doing a proper tube test because indications are it's needed. So I'm going to take this off. Hey, how come that was still showing 1.3 amps there? What happened there? Was it shorted right here? You know what? I think it was shorted right here. Right here. Don't you go anywhere. tape or anything in there. Pretty sure that's not shorted. Lid is closed. Current should be 0. Okay. The last time it was 0, we opened the lid, it started going. 1.3. Yeah, there can't be a short here because the switch is doing it. Shorted tube. Shorted capacitor. Shorted something. Something bad. Okay, let me just make sure I'm not drawing current from this battery anymore. I'm afraid a high voltage supply is not going to get exercised here. I'm going to have to do the tubes. Okay, that's what we'll do. I'm just going to take a little break and then we'll attend to that. Okay, first tube we're going to do is this one. Here, this one, according to the chart, is a 1S4. Looked up a 1S4. It's here. Power pentode. So this is the tube that drives the speaker. Used in output stage of lightweight, compact, portable, battery-operated equipment. 1S4 and 3S4 are identical except for filament arrangement. So using a 1S4 here because there's only one battery and only 1.5 volts available. So output tube first. Well, these are commonly ones that wear out because they tend to work hard. 1S4, it says right on it. Okay, 1S4. So I'll get this set up and we will test that tube. Okay, let's start out with a comparison between two of my cameras. Which one is doing a little better job here? This one or this one? Back to the first. About the same, aren't they? It's a little dark in here, so they're maybe having a little bit of trouble focusing. Okay, it's quite dark here. So here we go. This is double checking. This is a 1S4. And the setup here is 1S4. 1.5 volts on the filament. 2 signal level. 18H. 7. You know what? I got to be absolutely sure here. 73540. 73540. 73540. And P600. P600. Very good. 36. Meter adjustment. C for the plate. We're ready to go here on the first tube. These tubes basically heat instantly. As soon as you put the current to them, they're ready to go. So no warm-up time. And we're looking for short circuits. We have a short circuit here on setting number 1 on this tube. Now sometimes that's normal, not usually on an amplifier tube. So let's look. So here it says it has a key or a code here, F. Code F means you'll find a short on setting 1 during the short test. So that's nothing. So there's no shorts in this tube. Now does it work? The 1S4, P1 and P2. P1 and P2. Why 2 plates in here? Is this 1S4? That's just a little surprising. Let me just take a look. Why are there 2 settings there? 1S4. 1S4. Well, you see, the one plate is hooked up to 2 different pins. So there's two ways to get at the plate here. And for why, I have no idea why they did that, but they did. Okay, so that explains why there's two plate tests. Are you ready? Is everybody ready? GM test. This tube should come up to 1,000, just over 1,000. So 1,000's right there. We've got to beat that. She's a winner. That's it. This is a good tube. This is a very good tube. And this is the output tube. That's very good. Okay. Well, we're going to go after the next tube here. Set this one here. Now, do I really think I'll find a short in here that would account for the heavy current flow out of here? I don't know. 1S5. I think that's correct. 1S5. I've got to make sure these tubes are in the right spot too, because stuff happens. Okay, 1S2. 1S2, right? I didn't just mess the number up, did I? Of course I did. 1S5. Where did I get 2 from? 1S5. Doesn't take much. 1S5. Let's just carry right on here. 1.5. 2. 0. On the bias. I don't think I've ever seen that before. How come? 70043. 70043. 5600. 5600. 41. C. Also shows a short on pin 1. Okay, do we need to double check? We should. Because what happens is I start reading the wrong part of the chart here, and I'll end up setting this up half for one tube, half for another. 1S5. 70043. 7004 and 3. 5600, 5600. Yeah, we're good. There we go. Okay, any shorts? Just in the 1 position. We are ready. And what is it supposed to come up to? 410. Not very far up the scale. Just has to get past my finger. She's a good one. Yeah, that's good. And the P2 test should be... Oh, wait. Come on. Really? It does say this, doesn't it? P1 and P2. Am I reading that wrong? I don't think so. P1 and P2. P1 and P2. Well, that's a bit of a mystery. Maybe, yeah. No. What to think of that? Well, I think for now we have to assume it's good. I don't quite follow why it would test that way. Now we're going to put this one back in. Like I said before, it's very dark. It doesn't look dark in the camera. It's dark in here. Dark to my eyes anyway. Make sure that one's in. Oh, we don't want that popping open. Not that it matters, there's nothing hooked up. Now we need to get this one out. Not a lot of clearance here. There we go. This one is supposed to be 1T4. 1T4 it is. Made for General Electric Company Limited. So I don't think that's the original, because these would all be RCA tubes, wouldn't they? Be in an RCA radio? Half the business was selling vacuum tubes. to some degree they make a radio so they could sell tubes. To some degree. So this is the 1T4. 1T4. Let's just keep going here. 1T4. 1.520. 7340K. 7340K. 5600. 40 C. Okay, double check. 1T4. 7340K. 7340K. 5600. Okay. Here we go. Now what's that tube doing? Let me just peek at the so that's the IF amplifier tube. Right there. Okay. Does it have the F? Yes, it does. And it's got K1, K2. So 2 cathodes. Maybe the same thing. The cathode's connected to 2 pins. Let's see what this does. So just as expected. .580 is the reject point. 580 is about here. So it's just below the reject point. Nah, not really. I'd say it's right on the reject point. Now, back in the day, you might, let's get another tube in there, but in today's world, this tube is still good enough to do the job, that's for sure. No shorts in it. That's what I'm really looking for, is a shorted out tube. I don't know if this is going to work out. I have the feeling we're going to have to hunt down some other kind of problem. Let me put this one back in. Oh, this might be difficult to put in, so maybe I won't put it in. It's going to take too long. We'll just leave it hanging like that. We'll take this last one out. The last chance. Last chance for a short in the tube. Ooh, this is not coming out. There we go. It's supposed to be a 1R5, and it is a 1R5. This one says RCA Victor very proudly on it. Okay, Mr. RCA Victor. That would be an original tube. 1R4. Right there. 1.5. Says this is a diode. 70030. 70030. 0160. 0160. Just remember one of my cats is outside. In the cold, bad weather. 25, and this goes to A. Okay, double checking everything. This is a 1R5. So 1R4 is right there. Wait a sec. Triple checking here. Should be 1R5. Yeah, definitely 1R5. Then what did I set it up for? I bet you I set it up on 1R4. 1R5. 1520. Yeah, I did. 7345K. 7345K. So a mistake in setting these and sticking this tube in might ruin the tube like that. 7345K. 7345K. 5600. 5600. Wow. Am I doing this right? 645. Yep. C. Oh, yes, trouble was brewing there. Now I'm really nervous. One more double checking here. 1R5. I get the wrong numbers in my head and stuff when I'm doing this, especially with the video running. 1R5. One more check. 7345K. 7345K. 5600. 5600. Okay, I think we're good. 48. Yeah, 8 and 5 look the same. 48. See, we're good. I'm not nervous. Okay, so if there's a shorted tube, it's got to be this one. And this one also has a letter F? Yes. So we expect a short in position 1. Well, none of these tubes are shorted. So we will have to study up the circuit for the... yeah, we're going to have to get right into troubleshooting here, including probably capacitor replacement and everything before operating this radio. I don't like that. Okay, in this case, we are testing 910. 910, so just below the 1,000, right about there. She's a good one. Well, that's good. All the tubes are good. That is a good thing. I'm not sure these are the most common tubes around. Okay, so what we're going to have to do here is probably take the chassis out. This is all for tomorrow now. Take the chassis out, look at the situation, maybe choose to start changing a few capacitors or do some circuit analysis and try to identify which capacitor or component or what has happened to cause an apparent short circuit on the heater circuits. Because that's what it looks like. I'm thinking with this shorted, you get about 1.5 amps out of it. And that's roughly what we got. So I think that's really the case. We'll probably find a shorted capacitor in here. That's my guess. Well, thanks a lot for watching today. And as long as the sun doesn't shine, I will be in the shop in the morning. When the sun shines and the weather's good, I won't be in here. I'll be outside living my life. So thanks a lot for watching. See ya.